Okay, so previously we just talked about the rotation matrix between two frames. So let's see what can rotation matrix do more. Okay, so let's see the rotation of a vector. So in this figure, we have a vector p. And if we consider the vector p in the frame 1, we write it as p1. And if we consider this vector in the frame 1, we will need to do the projection to x1, y1, and z1. Okay, so if we do that, p1 and z1. Okay, so then we will be able to read the vector p in the frame 1. So assume that is u, v, and w, and u is projected to x1 and v is projected to y1 and w is projected to z1. Okay, so here if we want to consider the same vector that is in the frame 0, then I will need a vector p, and p can be written as u x1 plus v y1 plus w z1. Okay, so again, what is this? This is also dot product, right? And dot product, if we only know the vector length, and we can calculate dot product, okay? If we calculate the dot product between x and p, for example, these two, and it can be calculated by the length between these two and times the cosine angle, theta, right? And if we know the coordinates of x and p, we can also calculate it by these values adding together, right? So that are two methods of calculating dot product. One is from the absolute value, which is the length of these two vectors and the cosine angle, and one is from the coordinates, okay? So if we know the coordinates, we can also calculate the dot product between the same vectors. Okay, so here it goes back to, if we want to calculate p and we want to calculate projection, that is the dot product. Okay, and we know p1 is u, v, w. And if it is projected to x, y, and z, so that we can write p as this dot product. Okay, and then what is x1, y1, and z1? And again, x1 is a unit vector that is 1, 0, 0. Right? That is unit vector because this is x1 and it is a unit vector. So unit vector is still a vector and it is along x-axis. So along x, that is 1. And if it's perpendicular, that is 0. Okay, and y1, obviously, we talked about last time. That is 0, 1, 0. And z, of course, is 0, 0, 1. Okay, so then we plug in this p into the calculation. So if we want to calculate the p, the vector p, in the zero frame, with knowing that p1 is u, v, w as its coordinates, then we can do this calculation. Means we have the vector and now we project it to the zero frame, Okay, so then we plug in the p in the one frame, in the frame 1, so we'll have this term and dot product with x0, y0, and z0. Okay, and then we do one more step, and then it's interesting that we can have this term out. Okay, and then my p0 equals to a frame, a matrix like this times my u, v, and w. Okay, finally, That is, if we want to calculate P, the vector P in 0 frame, it equals to the rotation. We take a look at this matrix that seems very familiar. That is R10, right? R10. So it equals to R10 multiply P1. Okay, so it means by using the rotation matrix R10, we can rotate the vector P1 to P0. Okay, and one thing I want to emphasize that there is a little trick. So if we want to calculate the chain between rotation matrix, normally we can cancel here and here out. So it becomes P0, so there's only a 0 left. Okay, so then let's do one example. Okay, so this is an example that we have a block, and the block is rotating counterclockwise. Okay, so it's counterclockwise. We rotate from the original position and we do counterclockwise for 180 degrees, and then it goes to the new position. Okay, so then what is the rotation matrix? So the rotation matrix is that we are doing a rotation around the z-axis with the angle of 180 degrees. So if we write the rotation matrix of this action, that is, my rotation matrix is RZ with the theta equals to 180. Okay, so what is that? Do you still remember the basic rotation matrix which we just talked about it in part 1? Okay, so here is cosine theta, and this term should be sine theta, right? Sine theta. And this is negative sine theta, and this is cosine theta. And here is 0, 0, 1, 0, 0. Okay, so this is the basic rotation matrix with around z-axis with the theta, and in this case theta equals to 180. So then we plug in the theta value, so we have the calculation that is cosine 180, that is negative 1, 0, 0, 0. This is cosine, so that is okay. See here I have 0, and this is negative 1, and this is 0, and this 0, 0, 1. And because cosine 190 is 0, okay, so I have this rotation matrix. So what we're doing is we rotate the vector from PA to PB. So if we want to calculate PB, okay, we should know the rotation matrix multiply the original location, which is PA. Okay, so this should be R with the reference A and B. Okay, and this thing and A can cancel out, and this thing should be RZ. In this case, that is RZ 180, because the rotation action is around z-axis with the rotation of 180. Okay, so then I have my PA. Okay, so that's it. So this is another application of rotation matrix. So we can also use the rotation matrix to describe the rotation of something in the same frame. Okay, so this example is we rotate something in the same frame. Okay, so as a quick summary, so what can rotation matrix do? So the rotation matrix, we talk about the calculation, and there are applications of rotation matrix. So first of all, it represents a coordinate transformation relating the coordinates of a point P in two different frames. Okay, so it means if we want to calculate the same P in two frames, here I have frame 0 and frame 1, and this is P, the rotation matrix can relating the coordinates of the same P. Secondly, it gives the orientation of a transformed coordinate frame with respect to a fixed coordinate frame. And it means that, okay, so a frame can be rotated to a new frame with respect to a fixed coordinate frame. Okay, and the third thing is within the same coordinate system, we can rotate something. So this is a rotation of something in the same frame. Same frame. Okay, and this is rotation of frame. Okay, so that is a summary of rotation matrix, how we're going to use it in different applications. Okay, so next lecture we will talk about the next topic, which is the composition of rotations. So this lecture I will stop here of the calculation and the understanding of rotation matrix.